Here's the test station conducting the device characterization and integrated circuit evaluation. Here on the scope, it's a wafer we processed last year in BAE system, and we start another lot this year. I haven't finished yet, but I borrowed one from BAE, and you can look at and include the lot.
Yeah. Less Boeing?
Pardon?
BAE.
No, Jeff was talking about the Boeing and
we solved
from
that.
the laser.
We fixed that. And here's the device, and you can see here. The test station here has several functions. First, during the processing, we have an intermediate test to do the DC test. We see if the device performance reach our expectation. Then if everything's good, then we go to we return back and let them keep doing the lithography lift-off while it's about to make some RF test probe. Then we take back, do the RF high-speed test, RF test. Then that's our current status. And if it's the reason we send the wafer to BAE is to scale up, because basically here, because of the restriction of our tools, our equipment, we can only process small size of wafer like here. It's, when we grow some wafer here, 3-inch wafer, we cut into small pieces and we process here. We do the evaluation here, and we solve the problem one by one. And once we think that the process kind of mature, last year we sent the whole 3-inch wafer to BAE to see if there's any problem when we scale up the process.
What's the failure rate on those wafers now?
It's pretty small, but we didn't do any statistic analysis.
Okay.
But we test. It's very uniform. For the from characteristic point of view.
Okay.
It's a threshold. If we design the threshold at about 0.4, then it's about 0.35 to 0.5.
Okay.
But for the digital application, no any problem. But honestly, we didn't do yield analysis.
Okay.
That's really need almost automatic test station, because you set up a program, you let the computer to control the test station, and actually we ask code from test station vendor give us the semi-automatic test station for the future large-scale measurement use. Because that one you need maybe it's overnight measurement, automatically push down and measure, save the data, lift up, automatically move down, move up. Many devices. Then you do the analysis, but we haven't reached that point. And here are the results for this year's DC test. Because we already passed the DC process, and you can see here is about the gate length at the point A, and we can get a GM at 360. It's just for the N channel. The P channel, we have 2 micron, that's a pretty large one, and we get a GM 35. It's a pretty good result. And here here is results for the RF test from last year's, and here is the one result. It's about the gate length is 1.1. We get cutoff frequency is about 220. And you can see the GM is 180. Here we modify our structure and we do some improvement for our growth. And you can see the 0.8, it's about 20-30% shrink, but our GM increased almost double. GM increased double because theoretically it's a proportional. It's proportional. You shrink 30%, you increase 30%. But we shrink about 30%, we increase 100%. So we improve our growth. And here it's same result from here, but we use a little small devices about almost reach our current limit. It's about 0.6 or something. And we can get here it's about
0.6 micron.
Micron, right? But you know because the advantage of our POET technology is you can almost migrate silicon technology. Silicon, the processing is very similar. You can shrink down the gate length.
So silicon's at like 15 nanometers.
Oh yeah. We probably couldn't reach 50, but definitely behind 0.1 micron.
0.1 micron.
Yeah.
You're saying that when you go down by 30%, you double your frequency.
But it's double frequency.
Silicon was proportional.
But so here it's about 0.6 some kind of scale down, so we can get about 34-35. And so once we process a couple more runs, we are doing the laser now. We try to make laser work, and we use the same material, exactly same growth structure, and making this one. So once we get laser, and very soon we can get the integrated circuit, including laser, electrical, digital circuit, and detector. And then for the integrated circuit, we are going to test using the digital scope. You can see the diagram to see if what's a bit rate we can reach.